Okay, let's start. So it's my great pleasure to introduce Professor Yu from Caltech. So he will talk about mirror structure constants via non-Archimedean analytic disk.
Thank you very much for the introduction, and thank you for the invitation. It's my great pleasure to speak here. I'm sorry I couldn't come to the conference in person this time because I just had a newborn baby, but I will travel to Miami in January. So hopefully I will meet some of you in Miami in the January conference. Okay, the title of my talk is Mirror Structure Constants via Non-Archimedean Analytic Disks. It is work in progress with Sean Keel. I also shared the notes of my talk in the chat. And during my talk, if you have any questions or comments, please do not hesitate to interrupt me. Okay, let me start. Here's the plan of my talk. I'll start with motivations from SYZ and HMS, Strominger-Yau-Zaslow conjecture and homological mirror symmetry conjecture. And then I will explain the heuristics behind the mirror structure constants. After that, I will talk about non-Archimedean SYZ fibration, and then I will describe a boundary condition for the counts of these non-Archimedean curves. After that, I will discuss the properties of the moduli space and the ingredients in the proof of the main theorem. Finally, I would like to say some words on the comparison between punctured log Gromov-Witten invariants by Abramovich, Chen, Gross, and Siebert. And this log Gromov-Witten theory provides another approach to the construction of mirror structure constants. Okay, so let me start with motivations from SYZ and HMS conjectures. Definition, we recall a smooth projective variety over complex numbers, X over C, is called Calabi-Yau if its canonical bundle, Kx, is trivial. In other words, if it has a nowhere vanishing holomorphic volume form. So examples include elliptic curves, abelian varieties, K3 surface, hypersurface of degree d+1 in d-dimensional projective space. Mirror symmetry is a conjectural duality between Calabi-Yau varieties. It roughly says that for any Calabi-Yau variety X, there is a mirror variety X check such that a list of deep geometric relations hold between X and X check, involving Hodge numbers, Hodge structures, Gromov-Witten invariants, Fukaya categories, derived category of coherent sheaves, SYZ torus fibrations, etc. So, for example, in terms of Hodge numbers, we have HPQ of X is equal to H dimension minus P Q of the mirror X check. And in the three-dimensional case, the equality is reduced to just H11 of X equal to H12 of X check, and H12 of X is equal to H11 of X check. And we have this well-known diagram illustrating the statistics of the Hodge numbers for three-dimensional Calabi-Yaus discovered by physicists Candelas et al. Okay, that's a brief review of mirror symmetry. So today, we have two main conjectures in the study of mirror symmetry. One is the SYZ conjecture, named after Strominger, Yau, and Zaslow. And another is the HMS conjecture. It's homological mirror symmetry by Kontsevich. So now let me briefly review the two conjectures. First, we have the SYZ conjecture. Here's the rough idea. The conjecture predicts that in certain asymptotic sense, the Calabi-Yau manifold X should admit a torus vibration called SYZ vibration. We have the base and vibration by tori with possibly singular fibers, and they conjecture that for mirror symmetry purposes, the Calabi-Yau variety X, the Calabi-Yau variety X should admit in some limiting asymptotic sense this kind of vibration. We call it SYZ vibration. And the second, they say that the mirror manifold, the mirror Calabi-Yau manifold X check. So first they conjecture the existence of the vibration, and second, they want to say something about the geometry of the mirror. So they say that the mirror manifold X check is more or less the dual torus vibration, but after some corrections. So first, we just take the dual torus vibration, and then we make some corrections. They call instanton corrections. And it's given by some counts of holomorphic disks, some counts of open curves, like this. So the idea of the SYZ conjecture is to provide a geometric understanding of what the mirror looks like. Next, let's recall the rough idea of the HMS homological mirror symmetry conjecture. So we have the mirror pair X and X check. From X, the HMS conjecture defines a category called Fukaya category, denoted by Fuk-X. Objects of the category are Lagrangian submanifolds in X, together with some decorations, and morphisms are given by holomorphic disks with boundaries on these objects. So we see some relation between the instanton correction there and the morphisms here. And from X check, we consider the usual category of coherent sheaves. Then the homological mirror symmetry conjecture is the claim that if we take a derived category, then we should get an equivalence. Okay, yeah, that's the brief review of the two main conjectures in the field of mirror symmetry. Are there any questions at this point? Okay, so now if we combine the two conjectures, combining SYZ and HMS, we obtain a heuristic construction of the mirror variety X check. So I will illustrate this idea in my talk, but the best illustration of this idea is actually for the case of log Calabi-Yau varieties. Although physicists started with compact Calabi-Yau varieties, but in terms of mathematics, log Calabi-Yau varieties are somewhat easier to work with, and also in terms of applications, it has more applications. And furthermore, the reason that we illustrate this mirror construction in the log Calabi-Yau case is that in this case, the mirror will be an affine variety. The mirror X check will just be an affine variety, so that I can just describe it by its ring of functions, spec of some ring. We call this ring A the mirror algebra. And now, since we are describing the mirror as a spec of an algebra, and it suffices to describe the algebra, what we will do is to describe explicitly the underlying vector space of A, and then the multiplication rule. In other words, the structure constants. So in this log-Calabi-Yau case, the situation is particularly simple. The mirror will be just affine. So it's spec of an algebra, and then we will just be describing the algebra. We will write down the elements of the algebra and describe what is the multiplication rule for the elements. Let me remark that if you are not satisfied with the affine mirror variety, actually, we also have natural compactifications. And if you really want something projective, we construct also some graded algebra, and you take a project and you get the compactification. Okay, so now let me explain the heuristics behind the construction of mirror structure constants. Yeah, since we reduce the problem about mirror construction to just the problem of constructing some numbers. And as I explained, all the heuristics came from the combination of the SYZ conjecture and the HMS conjecture. And it's actually a long story about wall crossing, which eventually leads to the heuristic explanation that I'm going to give. Here is our setup. We have YD. Y is a smooth projective variety over K any field of characteristic 0, and D is a normal crossing divisor. We take U to be Y minus D, the interior. We review that among all volume, or among all top degree forms, or also pluriforms on U, we have this subset called log pluricanonical forms. And this subset consisting of log pluricanonical forms, they are independent of the compactification. And once we have this, we can give the definition of what is log-Calabi-Yau. So yeah, in the beginning, I gave the definition of Calabi-Yau, which is really simple. It's just the existence of nowhere vanishing volume form. Here, I'm saying that now we will be working with log-Calabi-Yau. It's like a non-compact version of Calabi-Yau. Then the definition is a little bit more involved. We say that the U is log-Calabi-Yau if for all M, this subspace of log pluricanonical forms is one-dimensional, and all of them are generated by a volume form, omega on U. It's no longer sufficient just to ask for a non-zero volume form in this case. We must also ask that all the log pluricanonical forms are generated by this volume form. You can just ignore this complication because we have you can only look at this example. So if in this case YD, for this pair YD, Y is a smooth projective D normal crossing, and if D lies D is an anticanonical divisor, D lies in the anticanonical class of Y, then U is log-Calabi-Yau. You will just satisfy this condition. So if you don't like this condition, you can just take this as your example of log-Calabi-Yau. just a smooth projective variety minus a normal crossing anti-canonical divisor. In this case, this pair YD is called the minimal model of U. And actually, all log-Calabi-Yau varieties arise in this way if we allow DLT singularities. If we don't just relax a little bit smoothness, then all log-Calabi-Yau varieties arise in this way. And actually, in our construction, we do need to use some minimal model program, but it's the technical part. The next definition that's important for us is the notion of maximal boundary. A log-Calabi-Yau U has maximal boundary if it has a minimal model with a zero-dimensional log-canonical center. So this is terminology when we have DLT. And in the normal crossing case, we are only asking for a zero stratum, meaning that we have many components of the divisor intersecting eventually at a point. So this is what maximal boundary means. And it's analogous to the maximal degeneration condition for Calabi-Yaus in mirror symmetry. And here for log-Calabi-Yau, we put this maximal boundary condition. Here is an example. If we have YD toric variety, then the interior is just the algebraic torus, and this is log-Calabi-Yau, simplest one. And more interesting ones can be given by the blow-up procedure. When we have this toric variety, we just blow up some points or subvarieties on the boundary. Here it's the surface case. We blow up some points on the boundary, and we get the pair. Y tilde is the blow up of Y, and the D tilde is the strict transform of D. And we take U tilde to be Y tilde minus D tilde, and this is again log-Calabi-Yau, just because D tilde is still anti-canonical in this case. So this is the simplest examples. We are the simplest examples. Now our goal is to construct the mirror variety X check. It's supposed to be affine. So we write X check equals spec A of any affine log-Calabi-Yau variety. And we are constructing, our goal is to construct the mirror variety for any affine log-Calabi-Yau. And we will construct the mirror algebra A by generators and also by structure constants. So here we assume affine. It's because without affineness, the mirror will not be affine, will just be a formal family. And furthermore, we will construct not just a single mirror, but actually a family of mirrors. Just more general, to have a family, and then we can say about the family. And if you really want a single mirror, you just take a fiber, for example. Okay. So now let me describe what's the mirror algebra. So what are the generators and what are the structure constants? Do you have any questions?
So just to be sure, you assume U is affine, right?
Yeah, I assume U as affine, and by mirror symmetry, for the mirror, I also get something affine. So this is,
oh yeah.
Yeah, so it's really affine going to affine.
I see. But when you blow up these 3 points in your picture above,
Yeah.
then this U tilde wouldn't be affine, isn't it?
Oh, yeah, that's a great question. So here it depends. If you blow up too much, it will not be affine anymore. That's true. Yeah. So if we blow up maybe 3 points, it's still okay. But if you blow up too many, it will not be affine. And in the non-affine case, we will have something, a formal family. Today, I will not be talking about this formal family, but we can also treat a certain formal case, which is with their more technical difficulties. For the moment, I just want to present the story between affine and affine.
But can I always, I mean, whenever I have low Calabi-Yau variety, and if I choose some ample of anti-canonical divisor, then I can always assume this is affine, isn't it? I think. If my anti-canonical divisor is ample.
Yeah, but not. Of course, if you have a projective variety and if the anti-canonical divisor is ample, then the interior will be affine.
Yeah. So.
Okay. Yeah, of course, yes. In general, the anti-canonical divisor may not be ample.
Right.
But let's concentrate first on the affine case. Okay, so yeah, so okay, so I will be describing. Thank you for the question. I will be describing now the generators and the structure constants. The generators, they are indexed by just a set. It's the set SKUZ called the set of integer points in the essential skeleton of U. What does it mean? If you know non-Archimedean geometry, you know this. Otherwise, we can give an explicit description, even if you don't know non-Archimedean geometry. So it's just 0 union multiples of so-called essential divisorial valuations on this field of rational functions on U. We can see, and essential means that our volume form has first order pole for this divisorial valuation. So it's just you for some divisorial valuation means it's valuation given by some divisor on some compactification of U, and we want the volume form to have first order pole along this divisor. Okay, and that will be the set for our generators. So more precisely, it's this thing. We have our base R. We will be constructing a family so that we have some base. The base will be generated by curves. You can ignore this because it's something about keeping track of curve classes. Since we are counting curves, we have homology class. So here the base will be generated by this ring of this monoid of curves, monoid ring of curves. In other words, it's sum of copies of Z parametrized by curve classes. And then we take A to be just the free R module generated by these integer points in the essential skeleton. Namely, it's direct sum of copies of R indexed by points of the essential skeleton. So it's free R module with basis SKUZ. Okay, so that's all for our algebra as a module. And next, we need to specify the multiplication rule. It means that given basis elements here, P1 to Pn, we write the product in the mirror algebra as follows. We write it the product theta P1 to theta Pn as as just we expand everything. So it will be an element in A, which means I can write it as sums over this basis. So we write it as sum over this basis theta q with q in all possible these integer points. And then we will get the element in R, since it's R algebra, and I also expand it. I write it as sum of basis over these curve classes, and then the coefficient, I get the integer coefficient, which we call structure constants. So now the question is, how do we construct these structure constants? As I mentioned, using the SYZ and the homological mirror symmetry conjecture, after a long story about wall crossing, one can somehow speculate that the structure constants are supposed to be given by the counts of the following holomorphic disks in U. So now let me describe what are the holomorphic disks here. Yeah, we have this data. What do we have in the parameter for the structure constants? We have this data P1 to PNQ. They are all elements of the SKUZ of these integer points in the essential skeleton, namely some divisorial valuation, and the gamma is some curve class. We can ignore for most of this talk, the curve classes. Okay, so as I said, each element Pj, it's just some integer multiple of some divisorial valuation if it's non-zero. And let's assume that this divisorial valuation is just given by a component of our divisor. We don't need to assume this, but for simplicity, let's do this. Then heuristically, the structure constant should be given by the number of holomorphic disks in Y satisfying the following conditions. First, we ask the disk to intersect every dj here, dj, with the given order mj. Mj is the multiple here. And the second, we ask that the boundary of our holomorphic disk maps to a point near Q. So yeah, so we have SYZ vibration, and we just project our boundary via this SYZ vibration, and we want the point to be close to Q. And then, okay, and next we need to use Q one more time. We ask that this boundary of the disk, so this is our disk, boundary is a circle. We ask the boundary to have homology class equal to Q inside the first homology of the fiber. Here we have SYZ vibration, and the fibers are tori. We can identify first homology of the fiber with some lattice, and this Q will make sense there. So we also ask the homology class to be equal to Q, and finally we ask the curve class of this disk to be equal to gamma. So this is what SYZ and the homological mirror symmetry would suggest. If we combine them together, they would suggest that the mirror should be constructed by the counts of such disks. However, it's just a very heuristic picture. In order to make the conditions, so we see that the conditions 2 and 3, they don't really make, they are not very precise, because here we didn't even say what is the SYZ vibration, and also there are many ambiguities here. So one way to make these conditions precise is that we we will replace the SYZ fibration by the non-Archimedean SYZ fibration. Because one reason for using non-Archimedean SYZ fibration is that it's canonical. When we have this data, initial data YD, we have a canonical non-Archimedean SYZ fibration, which is very easy to construct. And furthermore, for all things related to tropical curves or the projection via the SYZ fibration, they become particularly simple under the non-Archimedean SYZ fibration. Okay, now we will say something. Now I will say something about the non-Archimedean SYZ fibration. Do you have any questions so far?
So in your condition 3, can I choose any fiber?
Yeah. I choose the fiber, no, just for this fiber. Because this already maps to a point. So it's a fiber over that point.
I see.
Yeah, thank you for asking about it.
But I mean, is this fiber doesn't this fiber need to be a specific torus, special torus, something like non-displaceable torus?
It's a general point, so the fiber is just a general. It's a torus.
I see. So any
it's a
torus
smooth.
will.
Yeah, it's a smooth torus.
I see. So it doesn't have to generate the Fukaya category.
It doesn't. Here we don't depend on the Fukaya category.
I see. Thank you.
Thank you for the great question. Okay, so now I'm saying that I don't know how far one can go with these heuristics, since I'm not a symplectic geometer. But in my talk, we will make all this precise by going to the non-Archimedean SYZ fibration. Okay, so what is non-Archimedean here? It's very simple. We just equip our base field K with the trivial absolute value. So we set the norm of all non-zero element to 1 and the norm of 0 to 0. So then any field K, for any field K, if you do this, you get a non-Archimedean field. If it was complex numbers, we also treat complex numbers as non-Archimedean field. So once we get a non-Archimedean field and we have a variety over that, we can take so-called Berkovich analytification and we obtain a K-analytic space. Then we have a very rich theory of analytic geometry for such K-analytic spaces that is quite analogous to the theory of complex analytic geometry. So just if you never seen it before, just very quickly, this analytic space as a set, it consists of pairs, Xi nu, where Xi is a point in the scheme theoretic point, and the nu is the absolute value on the residual field extending the given one. Here we don't need to even extend the given one because K is just trivial. Okay, so roughly it's like enhancement of a scheme. We have scheme, we have all these scheme points, but these points are furthermore decorated with the absolute value or a norm. And this is our non-Archimedean space. And recall, we are working with Calabi-Yau, or Calabi-Yau, so we have our distinguished volume form. And since now we are in analytic geometry, we can take a norm of something. So for volume form, we also have a norm. It's written in Temkin's paper called the Kähler semi-norm, just the natural norm on the Kähler differentials. So we have this volume form, we take this Temkin's Kähler semi-norm, we get a function. In complex geometry, maybe it's continuous. Here we only get the upper semi-continuous function. And then the skeleton of U, SKU, is by definition the maximal locus of this upper semi-continuous function. Yeah, so here you see this is the definition of skeleton. It's really a very nice feature of this Berkovits analytification. And just now we had this, we defined by hand this SKUZ, the integer points in the essential skeleton, and actually it's just a subset in SKU. Because if you remember, we defined it by some divisorial valuation on the ring of, on the field of fractions, but the field of fractions is just the generic point. So it's a generic point plus a valuation, and it's part of the analytic space. And furthermore, it also maximizes this semi-norm. So as you see, once we interpret, we go to the non-Archimedean picture, the meaning of this basis is also clearer. So if it's the first time you see this, don't worry, because just the example, it's very simple. For example, if we look at this two-dimensional case, two-dimensional YD, like projective surface with this cycle of rational curves, then the essential skeleton SKU, maybe I should say essential skeleton here. The essential skeleton SKU is homomorphic to the dual intersection complex of D. Dual intersection cone complex, meaning that I have a ray for each irreducible component, and I have a cone here for each point, a node here. So using the works of Berkovits, Niges, Xu, and myself, we have a strong deformation retraction from the analytic space U to this skeleton. And this retraction is furthermore an affinoid torus vibration outside the codimension 2. So for this reason, we call it non-Archimedean SYZ vibration. And this is a canonical explicit construction. Here, affinoid torus vibration is the analog of this SYZ torus vibration, or the torus vibration in non-Archimedean geometry. And it means that locally, it's just this simplest version. You take analytic GM, analytic tori, or analytification of algebraic tori, and then you take, for each coordinate, you take a valuation. And you know, in the complex case, we have C star to the power n, and if you take norm, coordinate-wise, you get this torus vibration. Here, we just do it over a non-Archimedean field, and the resulting vibration, we call it affinoid torus vibration. So here is the picture. We have this analytic space, and we have the non-Archimedean SYZ vibration by this retraction here. It goes to the skeleton. Skeleton also embeds inside, but anyway, we have the skeleton here, and we have this retraction map. So it's the whole thing that deformation retracts to the skeleton. And then the fibers, they are this non-Archimedean affinoid torus. Here it's just it's not the topological space doesn't look like this, but it's like just a heuristic picture. And what's one thing that's really nice about the non-Archimedean SYZ fibration compared with the complex SYZ fibration is that whenever we have any analytical curve here, and when I project via this non-Archimedean fibration, I get something piecewise linear. And this piecewise linear gadget is usually called a tropical curve, the associated tropical curve. So in complex geometry, if you have a disk and or any curve you project by the SYZ fibration, you don't get this. You get so-called amoeba, and it's not easy to work with an amoeba. Okay. Okay, so now we replace the original SYZ fibration by the non-Archimedean version, and our goal is to construct the structure constants. So we recall, I just copy-pasted what I had before. Recall that the structure constants should be given by number of analytic disks in Y, satisfying the 4 conditions. We want the disk to intersect this the boundary with prescribed order of tangency, and we want the boundary of the disk to map to a point near Q via the SYZ fibration, and we also want the homology class, the boundary to have homology class Q, and furthermore we ask the class of the disk is equal to gamma. And now it was not. Now we can reformulate the conditions 2 and 3 in terms of the non-Archimedean SYZ fibration. So for conditions 2, it's the same. We ask it to. Yeah, what's nice is that now under the non-Archimedean SYZ fibration, the curve will just be this disk, analytic disk will project to a tropical disk, which is just a tree with a root. And we ask that this root goes near Q. And the fact that this has a homology class, the condition that the boundary has a homology class Q translates to the condition that the derivative of this, the derivative here at the root is equal to Q. Okay, so now we have these precise conditions, and we are ready to count analytic disks satisfying these conditions. But we have a trouble. When we want to count something, we consider the modular space of all these objects. The trouble we have is that the modular space of such disks is infinite dimensional. So we must impose further conditions to cut the dimension down to 0. We need the dimension 0 in order to get a finite count. So in particular, we must impose a regularity condition on the boundary of our disk to discard most of the non-Archimedean analytic disks. Because our structure constant is supposed to be the count of such disks. And now these conditions, we put some conditions, but they are not enough because we still have infinitely many. We need to put some more nice conditions so that we only get finitely many of them, and then that number will be what we are looking for. So here is the rough idea. What's really nice is that the boundary of the disk, it actually lies in the place with aphenoid torus vibration. Because we are asking the boundary to map to somewhere near Q, and it's kind of a general place. So at that general place, we know that our non-Archimedean torus vibration, SYZ vibration, is an aphenoid torus vibration, in the sense that locally it's isomorphic to this standard vibration. So we have this circle mapping to this standard thing, and we just want this map to be as simple as possible. Now, if we analyze some low-dimensional examples, we can propose the following boundary condition. We equip our circle. This is the, I shouldn't, it's fine. We equip this circle. I mean, strictly speaking, I shouldn't write boundary, but you just think it's the circle here. I equip my circle with the opposite orientation, and I want it to be the restriction of some map from a holomorphic disk to some toric compactification of this standard torus. And furthermore, we want that under this, when we have this map G from the disk to the toric variety, we want it to be straight. One can say that we want the associated tropical curve to be straight. Or one can also say that I also want it eventually just to hit one point at infinity. Okay, so now if we impose this boundary condition, it will work for when we look at some low-dimensional examples. Geometrically, it means the following. So I have my disk, and here I have this boundary circle. We are saying that if I equip the boundary circle with the opposite orientation, then I can extend it to another disk, this orange disk. And that orange disk will lie in this standard GM, standard torus. Eventually it will touch something outside, but that's not the issue. So geometrically, it means that we are gluing the toric variety Tn to my original projective variety Yn along some small domain G here, this gray area of trivial aphenoid torus vibration. And we denote the glued space by this Z. And now, in fact, we are counting closed rational curves, which is the gluing of this red disk, delta, with the orange disk, delta prime, along the circle here. I denote by A. We are counting such rational curves in the glued space Z. And we impose the condition that this red disk should still satisfy my previous conditions. And this orange disk should be straight. Yeah, so now the claim is that if we consider this straight or end as like a boundary condition here, then we should get a finite count of finite number of such red disks. And this number will be what we are looking for. So eventually, this finiteness is reduced to properness of the modular space. But although this idea, it's easy to say or draw, but we have, I mean, one may worry it's maybe not really realistic, because first of all, we glue along this domain and we get the target space. This target space will not be projective, and it's not even proper because it's not even separated. However you glue, either you choose to glue along something open or something closed. Here, in the non-Archimedean case, we will not be getting a separated space. So really, the question is, how is it ever possible to count curves in such a glued space? Because if the modular space behaves badly, there's no way to get a well-defined count. The idea is that as long as we can keep the circle here away from the boundary of the domain G, and recall that we were gluing our target space along this gray area G. So if we can keep this circle, so somehow the idea is that if we keep the circle kind of away from the boundary of G, then the rest of the curve should not feel the non-separated locus of the glued target space. I mean, all the worry we can have is like we are gluing along the gray area and we worry about the boundary of this gray area. But we hope, or the hope is that if we can control where this circle goes, and as long as this circle doesn't touch the boundary of the gray area, then the curve somehow cannot feel the boundary, because somehow it already, like this part of the curve already decided it should lie in Y, and that part of the curve already decided it should lie in T, and they do not see the trouble of the boundary anymore. More precisely, what we do is that we fix the marked point Q on the circle A, as well as marked points Pi, where the curve C touches the boundary of the varieties, the projective varieties, Y analytic and T analytic. And we consider the modular space, we denote by mu beta, the modular space of such curves inside the glued target space. And then we consider the map phi from the modular space to from the modular space by taking domain of my curve and the evaluation of this marked point Q. Okay, so we go to some subset, some domain in the modular space of pointed curves times this G times this gray area G. Yeah. Now I can state the main theorem of our work, which is this map phi is actually, we can prove that it's finite étale over an open neighborhood of the skeleton of the product here. So it's not finite étale everywhere, but it's finite étale over something kind of sufficiently big. And now we can take its degree for this finite étale map. And that degree gives the desired count of non-Archimedean analytic disks. And as I mentioned, that will just be our structure constant. And putting these structure constants together, we obtain a commutative associative mirror algebra, A. So furthermore, we prove that the mirror family we obtain we also prove geometric properties of the mirror family we obtain. We prove that it is a flat family of Gorenstein SLC log Calabi-Yau varieties. And furthermore, the generic fibers are normal and log canonical. Yeah, so that's the main result. And in the last 5 minutes, let me say something about the ingredients in the proof of the main theorem. So we prove that this map phi, so after doing all this complication, having all these complication about the boundary conditions and so on, we eventually show that this phi is finite et al. And finite et al. Is the combination of 3 properties: smooth, relative dimension 0, and proper. For smoothness, we had to use some non-Archimedean deformation theory that I developed together with Mauro Porta. Because here, we have to have a deformation theory for these non-Archimedean curves in the non-Archimedean space, which is not necessarily algebraic. So then when we consider like cotangent complex, so on, it has to be considered with the analytic structure. From this, we get the smoothness. And the next, for the computation of virtual dimension, that's also a bit tricky, because before we have this, we started with log Calabi-Yau, and the log Calabi-Yau is important. This condition is important in order that we have the right virtual dimension for the counts. Here we glued something arbitrary there, we may lose this log Calabi-Yau condition. So we also need to take care of the volume form here, that we also glue somehow to volume forms. And the trickiest part is the properness part. So we recall that in analytic geometry, proper actually is the combination of 2 things. One is that it's topologically proper. It's proper as topological space, as a map between topological spaces, and then another is that it's without a boundary. We call it a boundaryless. So you can just think, for example, in complex geometry, if we have a closed unit disk, although it's compact, but you don't want to call it a proper because it has a boundary. You only want to call something like a projective line, a sphere, to be proper. You don't want to call a closed unit disk to be proper. Here it's the same. It's a combination of topologically proper and boundaryless. And both have to be proved using formal models. In fact, we need to introduce an auxiliary moduli space, which we denote by M prime U beta, which, so that moduli space asks not only the circle A to map to the gray area G, but it also asks an open thickening of the circle to map to G. And the idea is that for one moduli space, we will get topologically proper. And for that, the other moduli space here, prime version, we get boundaryless. But eventually, we need to kind of identify these two. So finally, we use the theory of skeletal curves to identify these two moduli spaces. But we can only identify them. We cannot identify them in general. We can only identify them over the skeleton of this target. So the geometric idea is that one moduli space is only asking this circle to go to the gray area. And another moduli space is asking not just a circle, but a thickening. It's like a thicker annulus to go to this gray area of aphenoid torus fibration. But how can we identify them? We need to prevent bad branches from growing out of the annulus when we pass by walls in the skeleton there. In the skeleton. So this purple branch, if we have this purple branch here attached to the thickening of the circle, that's bad for us. Then we will not be able to identify these two. So the way we prevent it from happening is to use the theory of skeletal curves. I guess I out of time, and maybe next time I will talk more about the comparison and other related other related topics. Yeah, thank you very much for your attention.
Thank you very much for the talk. So is there any question, comment? Could you briefly just go through section 7 very briefly, what you are trying to say?
Yeah, you mean for comparison?
Yeah.
Yeah, I think for comparison, now it's also possible to prove, to do it, because it's still very mysterious that, so the logarithmic approach is working, so for the moduli space and everything, the logarithmic approach is really working at the level of spatial fiber. And here, when we are setting up all the story, at many places, we also use formal model. So in some sense, we already have all the we already also set up everything at the level of spatial fiber. Then in order to compare with the logarithmic approach, one thing one can do is that one can also put this tail condition at the logarithmic approach, and then the comparison will only be at the level of closed rational curves. But yeah, and it's really surprising that when we only consider the spatial fiber, somehow we don't need extra boundary conditions. But here, as I said, if we look at these some low-dimensional examples, one can see that from the non-Archimedean picture, we really have too much freedom. If we don't impose the boundary condition, we really have too much freedom for the coefficients of these maps. And if we want to kill this freedom, it amounts to putting this boundary condition. So maybe this is what I can say for the moment.
Thank you.
Thank you.
So is there any possibility to generalize your works over the discrete value field?
Oh, yeah, sure. It also works for, yeah. Here we are doing it. Yeah, it's a great question here. Why we do this for this trivial absolute value? It's mainly for expository purposes, because people are interested, because people are interested in varieties over complex numbers. So here we just do the take the trivial valuation over complex numbers. But actually, in the theory, this K, we have to make field extensions to non-trivial discrete valued fields. And also the theory of non-Archimedean geometry for this trivial valued field, it's actually also based on the theory of non-trivially valued field, because in setting up the theory for many proofs, usually it goes like you make an extension and assume that it's non-trivially valued.
Okay, so is there any other question or comment? Okay, if not, let's thank the speaker again.
Thank you.